The 7th of September, 1940, dawned gray and turbulent over the English Channel. Squadron leader Douglas Bader banked his Supermarine Spitfire hard to starboard, his eyes scanning the horizon for the expected Luftwaffe formations. Behind him, 12 more fighters from RAF Duxford's 12th Squadron maintained tight formation, their Rolls-Royce Merlin engines thundering through the morning air. What the German High Command did not yet understand, what they would learn through blood and wreckage in the months ahead, was that British fighters now carried a weapon that would fundamentally alter aerial warfare. The Hispano Mk 2 20mm cannon, nestled in each Spitfire's wing, represented a technological leap the Luftwaffe had grievously miscalculated. German intelligence reports from late 1939 had predicted disaster for any British adoption of cannon armament. Reichsmarshal Hermann Göring himself had reviewed assessments concluding that the temperamental nature of aircraft-mounted automatic cannons would render them ineffective in combat conditions. The German Messerschmitt Bf 109E fighters carried the Mauser MG 151 cannon, but even this weapon suffered frequent jamming problems when subjected to the extreme G-forces and vibrations of dogfighting. Luftwaffe tacticians reasoned that if Germany's precision-engineered weapons struggled with reliability, surely the British, perceived as mechanically inferior, would fare far worse. This assumption rested on historical precedent. During the First World War, aircraft-mounted automatic weapons had proven notoriously unreachable. Freezing temperatures at altitude caused lubricants to congeal, while the violent maneuvering of combat flying induced mechanical failures. The interwar years saw numerous failed attempts to mount cannons on fighter aircraft across multiple nations. France's early experiments with Hispano cannons in the mid-1930s had resulted in embarrassing failures during field trials, with jam rates exceeding 40% during mock combat scenarios. What German intelligence failed to comprehend was the quiet revolution occurring at the British Small Arms Company facility in Enfield and at Hispano-Suiza's manufacturing plants. Marc Burckett, the Swiss engineer who had designed the original Hispano-Suiza cannon for the French Armée de l'Air, had not accepted his weapon's initial shortcomings. Throughout 1938 and 39, Burckett and British engineers worked obsessively to redesign the cannon's feed mechanism, breech assembly, and firing pin configuration. According to documentation from the Royal Aircraft Establishment Archives, referenced in Jonathan Glancy's comprehensive study, Spitfire, the illustrated biography, published by Atlantic Books in 2006, the breakthrough came when engineers modified the drum magazine system to accommodate belt-fed ammunition, dramatically reducing the weapon's tendency to misfeed during high-G maneuvers. The Hispano Mk II emerged from these modifications as something unprecedented in aviation history. The cannon fired a 20mm high-explosive incendiary shell at 600 rounds per minute, a rate of fire that combined devastating stopping power with remarkable mechanical reliability. Each shell weighed 4 ounces and contained a bursting charge sufficient to tear through aircraft aluminum, sever control cables, and ignite fuel tanks. Where 8 Browning 303 caliber machine guns might require sustained fire to bring down a bomber, a single well-placed burst from a Hispano cannon could shatter an aircraft's structural integrity in seconds. Flight Lieutenant James Ginger Lacey of 601 Squadron first encountered the weapon's effectiveness on the 15th of August, 1940, during a massive Luftwaffe raid against RAF Hawkinge. Engaging a formation of Dornier Do-17 bombers over Canterbury, Lacey fired a 3-second burst from his cannon-armed Spitfire at a range of 300 yards. The results astonished him. The German Technisches Amt, the Luftwaffe's Technical Procurement Division, had conducted extensive analysis throughout 1939 regarding Allied aviation armament development. Senior engineers like Oberstleutnant Ernst Heinkel maintained detailed intelligence files on British weapons programs, particularly focusing on the Royal Air Force's transition from rifle-caliber machine guns to heavier armament. Their conclusions, documented in captured Luftwaffe records now housed at the Imperial War Museum, reflected a curious mixture of technical understanding and cultural bias. German test pilots who had defected from Republican forces during the Spanish Civil War provided first-hand accounts of early Hispano cannon failures. During the Battle of Tarawa in late 1937, Soviet-supplied Polikarpov I-16 fighters equipped with prototype Hispano-Suiza cannons had experienced catastrophic jam rates, sometimes rendering the weapons completely inoperable after mere seconds of firing. These reports circulated through Luftwaffe intelligence channels, reinforcing existing prejudices about Allied engineering capabilities. What the Germans failed to recognize was the systematic nature of British problem-solving. At the Royal Aircraft Establishment in Farnborough, a dedicated team under Wing Commander Ralph Sorley had established exacting testing protocols for the Hispano Mk. Unlike the hasty Spanish Civil War deployments, British engineers subjected each component to thousands of hours of controlled testing. They fired cannons mounted on specially designed vibration tables that simulated combat maneuvers. They tested weapons in refrigerated chambers that replicated high-altitude temperatures reaching -40 degrees Fahrenheit. They analyzed high-speed photography of the firing mechanism to identify microscopic timing errors. The breakthrough modification involved redesigning the cannon's recoil spring and buffer system. Original Hispano designs used a single heavy spring that occasionally failed to return the breech block with sufficient force during rapid fire sequences. British engineers, working closely with metallurgists from Sheffield's steel industry, developed a dual-spring system with precisely calculated tension coefficients. This modification, combined with improved ammunition belt links manufactured to tolerances of 1/1000th of an inch, reduced the jam rate from 40% to less than 2% under combat conditions. Squadron leader Peter Townsend, who would later gain fame during the Battle of Britain, participated in early operational trials of cannon-armed Spitfires with 43 Squadron in February 1940. His combat reports, preserved in the National Archives at Kew, provide detailed assessments of the weapon's performance. On one sortie over the North Sea, Townsend engaged a Heinkel He-111 reconnaissance aircraft at 18,000 feet. His cannon fire struck the bomber's port engine, and the explosive shells detonated with such force that the entire engine nacelle separated from the wing within 2 seconds. The psychological impact on Luftwaffe crews proved as significant as the physical damage. German bomber pilots who survived encounters with cannon-armed British fighters reported their experiences to intelligence officers with barely concealed terror. Unteroffizier Klaus Weber, a Dornier Do-17 pilot shot down over Kent on the 18th of August, 1940, described the cannon attack during his interrogation at the Combined Services Detailed Interrogation Center. His bomber had taken a single cannon hit to the starboard wing root. The explosive shell had detonated inside the wing structure, instantly destroying hydraulic lines, fuel tanks, and primary control cables. The aircraft became unflyable in less than 5 seconds. By contrast, German MG-151 cannons, while theoretically comparable in destructive power, suffered persistent reliability issues that pilots had learned to accept as inevitable. The 20th of August 1940 marked a turning point in aerial combat doctrine that German planners had not anticipated. Over the chalky cliffs of Dover, Flying Officer Alan Deere of 54 Squadron engaged a shawarma flight of 4 Messerschmitt Bf-109E fighters in what would become a textbook demonstration of cannon armament superiority. Deere's Spitfire, one of the newly delivered Mark IB variants equipped with 2 Hispano Mk. Cannons, supplemented by 4 Browning machine guns, possessed a firepower concentration that fundamentally altered the mathematics of air combat. Traditional fighter tactics developed during the interwar years assumed that pilots needed sustained firing opportunities to achieve kills. The standard deflection shooting techniques taught at RAF flying schools emphasized leading the target and maintaining fire for 3 to 5 seconds to ensure adequate hits. These doctrines had evolved around the 8-gun Browning armament package, which delivered approximately 160 rounds per second of 303 caliber ammunition. While devastating in volume, these rifle caliber rounds often passed through aircraft structures without causing immediate catastrophic damage. The Hispano cannon inverted this tactical paradigm entirely. A single 1-second burst from two cannons delivered 20 high-explosive shells, each capable of independent destructive effect. Pilots quickly learned that accurate gunnery mattered far more than sustained fire. Flight Lieutenant Robert Stanford Tuck of 92 Squadron became one of the early masters of cannon tactics, developing firing techniques that maximized the weapon's explosive potential while conserving ammunition. German bomber formations began modifying their defensive tactics specifically to counter cannon-armed fighters by mid-September 1940. Luftwaffe tactical manuals issued to Kampfgeschwader units instructed pilots to maintain tighter formations, reasoning that concentrated defensive machine gun fire might deter British fighters from pressing attacks to the close ranges where cannon fire proved most deadly. This tactical adjustment, however, created its own vulnerabilities. Tighter formations meant less maneuverability and increased collision risks, particularly when under sustained attack. The Luftwaffe's doctrinal response revealed a deeper misunderstanding of the cannon's operational characteristics. German intelligence officers analyzing gun camera footage recovered from downed British aircraft initially concluded that the Hispano Mk suffered from limited ammunition capacity. This assessment was technically accurate. Early Spitfire Mark 1B variants carried only 60 rounds per cannon, providing approximately 10 seconds of total firing time. However, German tacticians failed to appreciate that 10 seconds of cannon fire represented far more combat effectiveness than 30 seconds of machine gun fire. Wing Commander Douglas Bader, commanding the Duxford Wing, exploited this German miscalculation throughout September's major engagements. Bader's tactical philosophy emphasized altitude advantage and concentrated attack, with cannon-armed Spitfires assigned to attack bomber formations while machine gun-equipped fighters engaged Messerschmitt escorts. On the 15th of September, the date later commemorated as Battle of Britain Day, Bader's wing intercepted a massive raid comprising approximately 150 Dornier and Heinkel bombers, escorted by over 200 Messerschmitt fighters. The engagement unfolded over South London between 1200 and 1300 hours. Squadron leader Michael Robinson of 229 Squadron, flying a cannon-armed Spitfire, attacked a Staffela squadron of 9 Dornier Do-17 bombers maintaining formation at 19,000 feet. The Hispano Mk.II's internal mechanisms represented a triumph of precision engineering that German weapons designers had deemed impossible under combat conditions. At its core, the cannon operated on a gas-operated, automatic firing system that harnessed explosive gases from each fired round to cycle the weapon's breech and chamber the next shell. This fundamental principle, while theoretically simple, required extraordinary manufacturing precision to function reliably under the punishing conditions of aerial combat. Inside the Hispano-Suiza factory at Gennevilliers, France, before the German occupation, Mark Burkett had personally overseen the manufacture of prototype breech assemblies. Each component underwent individual inspection with precision, measuring instruments calibrated to 10,000ths of an inch. The barrel itself, machined from chrome molybdenum steel, featured rifling grooves cut at precisely 3 degrees 45 minutes of arc, designed to impart optimal spin stabilization to the 20mm shells while minimizing barrel wear. British manufacturing facilities at Birmingham Small Arms Company and Royal Ordnance Factory Nottingham replicated and improved upon these French production techniques. Chief Engineer Harold Cardwell, who supervised Hispano production at Birmingham, implemented statistical quality control methods borrowed from American automotive manufacturing. Every 10th cannon produced underwent destructive testing, being fired continuously until mechanical failure occurred. These tests, conducted at RAF Shoeburyness Proving Grounds, typically resulted in barrel failure only after 15,000 to 20,000 rounds, far exceeding the weapon's expected combat lifespan. The ammunition feeding system presented the most significant engineering challenge. Early designs employed 60-round drum magazines mounted above or below the cannon body. While mechanically simple, drums introduced weight distribution problems and proved vulnerable to centrifugal forces during violent combat maneuvers. The solution came from studying the successful belt feed mechanisms used in ground-based anti-aircraft guns. British engineers designed a flexible disintegrating link belt system using phosphor bronze links, each precisely manufactured to hold a single 20mm shell at the exact angle required for smooth feeding into the breech. German intelligence obtained detailed technical drawings of the Hispano Mk through espionage efforts in neutral Switzerland during early 1940. These documents, delivered to the Reichsluftfahrtdienst, the Reich Aviation Ministry in Berlin, should have alerted German planners to the weapon's capabilities. However, institutional bias and overconfidence in existing Luftwaffe equipment prevented proper assessment. General Oberst Ernst Udet, chief of the Luftwaffe's Development and Procurement Office, dismissed the drawings as either fraudulent or representing impractical prototypes unlikely to achieve operational status. This assessment proved catastrophically wrong. By late August 1940, RAF Fighter Command had deployed over 200 cannon-armed Spitfires across southeastern England. Pilots reported jam rates below 3%, even during extended combat missions. The weapon's reliability under actual combat conditions exceeded even optimistic British projections. Flight Sergeant George "Grumpy" Onwin of 19 Squadron flew 15 combat sorties during the first week of September without experiencing a single cannon malfunction, firing over 400 rounds in total. The explosive shells themselves deserved equal credit for the weapon's effectiveness. Each 20mm round contained a precisely measured charge of penterythritol tetranitrate explosive, commonly known as petin, weighing approximately 0.2 ounces. Upon impact, a piezoelectric fuse detected the sudden deceleration and initiated detonation within 0.02 of a second. The 3rd of September 1941 marked exactly 1 year since Britain's declaration of war against Germany, and the accumulated combat reports from RAF squadrons painted an irrefutable picture of the Hispano Mk2's operational superiority. At RAF Bentley Priory, Air Chief Marshal Hugh Dowding's Fighter Command Headquarters, intelligence officers compiled statistical analyses from over 1,200 confirmed aerial victories. The data revealed patterns that contradicted German assumptions so fundamentally that Luftwaffe intelligence officers initially suspected British disinformation. Pilot Officer Eric Locke of 41 Squadron exemplified the cannon's combat effectiveness through documented precision. Locke, a quiet Shropshire farm boy who had joined the RAF in 1939, achieved 16 confirmed kills between July and September 1940. His combat reports, meticulously filed with Fighter Command Headquarters, described engagements where single cannon bursts destroyed enemy aircraft within seconds. On the 5th of September, Locke engaged a Junkers Ru-88 bomber over Southampton at 17,000 feet. His gun camera footage, analyzed frame by frame at RAF Farnborough, showed his 3-second cannon burst striking the bomber's cockpit area. The explosive shells penetrated the glazing and detonated inside the crew compartment, killing all 4 occupants instantly and severing primary control cables. The Junkers entered an inverted spin and impacted the English Channel 28 seconds after Locke's attack. German bomber crews developed superstitious behaviors attempting to avoid cannon-armed fighters. Obergefreiter Hans Schmidt, a Heinkel He-111 wireless operator shot down over Hampshire and captured on the 11th of September, described elaborate pre-mission rituals his crew had adopted. They had begun wearing double life jackets after learning that cannon explosions often destroyed standard flotation equipment. They carried extra morphine ampules for treating shrapnel wounds from shell fragmentations. Some crews even wore captured British steel helmets under their flight caps, hoping the additional armor might provide protection against explosive shells, a futile gesture given the shell's destructive power. The Luftwaffe's own casualty statistics, discovered in captured documents after the war, confirmed the cannon's disproportionate lethality. According to records from Luftflotte 2, the German air fleet responsible for operations against southeastern England, aircraft damaged by cannon fire had a 73% probability of total loss, either through immediate destruction or forced landing in enemy territory. By contrast, aircraft damaged by machine gun fire showed only a 41% loss rate. Many machine gun-damaged aircraft returned safely to French airfields, despite extensive bullet holes, while cannon damage typically meant catastrophic structural failure. Squadron leader Adolphe Sailor Malin, the South African ace commanding 74 Squadron, pioneered systematic cannon gunnery training that maximized the weapon's potential. Malin recognized that pilots trained on machine gun tactics instinctively fired long bursts from excessive ranges, wasting precious cannon ammunition. He established a training protocol at RAF Hornchurch requiring pilots to practice gun camera attacks against target drogues towed by Westland Lysander aircraft. Pilots learned to close within 250 yards before firing, ensuring maximum hit probability with minimal ammunition expenditure. This disciplined approach to cannon employment produced remarkable results. Malin himself achieved 27 confirmed victories during the Battle of Britain period, with cannon fire accounting for 19 of those kills. His tactical reports emphasized the psychological advantage of cannon armament. German pilots, he noted, often broke formation upon seeing a cannon-armed Spitfire approaching, even before the British fighter opened fire. By October 1940, the Reichsluftfahrtdienst could no longer ignore the mounting evidence of British cannon superiority. Oberst Joseph Pips Priller, a highly decorated Luftwaffe fighter ace commanding Jagdgeschwader 26, submitted a lengthy tactical assessment to Luftwaffe High Command headquarters in Berlin. Priller's report, based on interviews with over 50 pilots who had engaged cannon-armed British fighters, painted a sobering picture that contradicted every pre-war assumption about aircraft armament. The document, entitled Analysis of RAF Fighter Armament Effectiveness and Recommended Countermeasures, ran to 47 pages and included appendices with technical diagrams reconstructed from gun camera footage and wreckage examination. Priller noted that British cannon shells appeared to detonate with greater reliability than German MG 151 rounds, suggesting superior fuse design or explosive composition. He recommended immediate prioritization of improved German cannon development and the retrofit of existing Messerschmitt Bf 109 fighters with more reliable weapon installations. General Oberst Ernst Aditt, despite mounting evidence, resisted fundamental changes to Luftwaffe armament programs. Aditt's technical background, he had been a First World War ace and aerobatic display pilot, inclined him toward conservative engineering approaches that emphasized proven designs over experimental innovations. His personal relationships with German industrialists, particularly those at Mauser and Rheinmetall, who manufactured existing Luftwaffe weapons, created institutional resistance to admitting that British engineers had achieved superior results. The bureaucratic inertia within German military-industrial complex proved more damaging than any British tactical advantage. Proposals to license-produce Hispano cannons using captured examples from downed British aircraft languished in procurement committees throughout late 1940 and early 1941. Engineers at Mauserwerk in Oberndorf conducted technical evaluations of recovered Hispano Mk cannons but concluded that German manufacturing facilities lacked the precision tooling necessary to replicate British production tolerances. This assessment, while technically accurate regarding existing German capabilities, represented an admission that the Reich's celebrated industrial infrastructure had been surpassed by British engineering. Alternative development programs fared little better. The Mauser MG 213 cannon, designed as a German response to the Hispano's effectiveness, entered development in early 1941 but suffered from the same reliability problems that had plagued earlier German cannon designs. The weapon used a rigid belt feed system that jammed frequently under high-G maneuvers. Prototypes installed in Focke-Wulf FW-190 test aircraft showed jam rates exceeding 15% during mock combat trials at Rechlin Proving Grounds. By the time engineers resolved these issues, production priorities had shifted to other weapon systems, and the improved MG 213 never achieved widespread deployment. Meanwhile, RAF Fighter Command expanded its cannon-armed fighter force systematically. By January 1941, over 60% of operational Spitfire squadrons flew the Mark V variant, which carried 2 Hispano Mark II cannons and 4 Browning machine guns as standard equipment. The Hawker Typhoon, entering service in mid-1941, mounted 4 Hispano cannons, providing unprecedented firepower for ground attack and anti-shipping operations. The operational impact extended beyond fighter versus fighter combat. Cannon-armed Spitfires and Hawker Hurricanes proved devastatingly effective against German shipping in the English Channel. The explosive shells could penetrate light vessel armor and detonate inside crew compartments or engine spaces, destroying E-boats and cargo vessels that would have survived machine gun attacks. The 15th of March, 1942, witnessed the Hispano Mk2's evolution from air superiority weapon to multi-role armament system. Over the French coast near Boulogne, squadron leader Brian Kinkham led 92 Squadron on a low-level shipping strike against German coastal convoy. The 12 Spitfire Mark V fighters dove from 8,000 feet, their cannons targeting a group of armed trawlers and E-boats transiting between Le Havre and Calais. The engagement lasted 90 seconds and resulted in 3 vessels sunk, 2 severely damaged, and no British losses. This tactical flexibility emerged from systematic experimentation by RF, Coastal Command, and Fighter Command units throughout 1941. Wing Commander Denis Gillam, commanding the Exeter Wing, pioneered combined cannon and rocket projectile attacks against German shipping and coastal installations. His pilots discovered that cannon fire could suppress German anti-aircraft positions, creating gaps in defenses that allowed rocket-armed Typhoons to attack with greater accuracy. The cannon's flat trajectory and explosive payload made it superior to bombs for precision attacks against small, maneuvering targets. German coastal defense forces quickly learned to recognize the distinctive sound of 20mm cannon fire. Oberleutnant Zersi Martenstahl, commanding a R-boat German motor minesweeper flotilla based at Dunkirk, described the psychological terror of cannon attacks in his patrol logs. Unlike machine gun bullets that produced sharp pinging sounds when striking steel hulls, cannon shells detonated with concussive force that shook entire vessels. Sailors below decks often suffered ruptured eardrums and concussive injuries even when shells exploded externally against hull plating. The weapon's effectiveness against ground targets exceeded initial British expectations. During the Dieppe raid on the 19th of August 1942, cannon-armed Spitfires provided close air support for Canadian infantry storming German fortifications. Pilots discovered that cannon shells could penetrate concrete bunkers up to 8 inches thick, something rifle-caliber machine gun fire could never achieve. Flight Lieutenant John "Johnny" Johnson of 610 Squadron conducted repeated strafing runs against German pillboxes overlooking Red Beach, his cannon fire opening breaches that allowed infantry to advance with reduced casualties. Technical improvements continued throughout 1942 and 43. The Hispano Mk V variant entered production in mid-1942, with several refinements addressing field experience feedback. Engineers lengthened the barrel by 4 inches, increasing muzzle velocity from 2,850 to 3,000 feet per second and improving armor penetration characteristics. The upgraded feed mechanism accepted longer ammunition belts, providing 20 seconds of firing time compared to the Mark II's 10 seconds. American adoption of the Hispano cannon, designated M2 in U.S. military nomenclature, initially stumbled due to manufacturing challenges. The United States Army Air Forces ordered large quantities of license-produced cannons in 1941 for installation in P-38, Lightning and P-39 Airacobra fighters. However, American manufacturers struggled to replicate British manufacturing tolerances, resulting in jam rates exceeding 20% in early production models. Only after British technical advisors established quality control protocols at American factories did reliability improve to acceptable levels. By mid-1943, the Hispano cannon had become the Allied standard aircraft weapon, installed in British, American, Canadian, Australian, and Free French aircraft. Total production exceeded 100,000 units across multiple manufacturers. The weapon-armed Supermarine Spitfires, Hawker Typhoons, and Tempest de Havilland Mosquitoes, Bristol Beaufighters, Lockheed P-38s, Bell P-39s, and P-63 Kinkabreys, and North American P-51 Mustangs. The 8th of May, 1945, brought victory in Europe Day and the end of the Third Reich. In the bombed ruins of Luftwaffe headquarters buildings across Germany, Allied intelligence teams discovered warehouses filled with technical reports, combat assessments, and procurement documents that told a remarkable story of institutional failure. German military engineers had possessed accurate intelligence about the Hispano Mk II's capabilities as early as October 1940, yet bureaucratic resistance and industrial limitations prevented effective response throughout the war's entire duration. Among the recovered documents, a particularly revealing report from Recklinler's airfield's test facility dated the 4th of November, 1943 provided devastating analysis. German engineers had conducted comparative trials between a captured British Hispano Mk II cannon and the latest German MG 151-20 variant. The tests involved mounting both weapons on vibration simulators that replicated combat flight conditions while firing continuously. The Hispano fired 1,500 consecutive rounds with 0 stoppages before testing ceased due to barrel heat limitations. The MG 151 experienced 14 jams during the same test protocol, requiring manual clearing each time. German engineers concluded that British manufacturing precision exceeded German capabilities by measurable margins, particularly in component dimensional tolerances and heat treatment processes. This technical superiority stemmed from Britain's systematic application of scientific management principles to weapons manufacturing. The wartime collaboration between British engineers, metallurgists, and production managers created quality control systems that Germany's fragmented industrial structure could not match. While German factories maintained high manufacturing standards for showcase,